cloud. Okay, so today's lesson is on 2.4, excuse me, and this deals with imaginary and complex numbers. So here with this, a complex number is a number that is made up of both a real and an imaginary part. So the real part will always be what we lead with. It will always be in the form A plus BI, where the BI is the imaginary part and the A is the real part. So that's why it's called a complex number. It has both real and imaginary parts to it. Complex conjugates are a pair of complex numbers in the form A plus BI and A minus BI. So whenever I talk about a complex conjugate, you want to change the sign in front of the imaginary part. That will be your complex conjugate. And we'll do that with whenever we have fractions or division happening with imaginary numbers. We don't like to leave I in a denominator. So we'll see how to take care of that with the complex conjugate. So some more vocabulary. Oh, I did not plug in. Send to my smartboard. Give me 1 second. There we go. Should respond soon. Okay. So mathematicians create an expanded system of numbers using the imaginary unit I. I forget exactly when it happened. I want to say it was in the 1500s. A mathematician took the time, went through all the math behind it, and actually showed that, wait, if we define I as the square root of -1, this is how we can operate with it as a number. So I is defined as the square root of -1 because we cannot take the square root of negative numbers. So for centuries, mathematicians have been running into problems where we would end up taking the square root of a negative and we would just say, well, it has a square root of negative. There's no answer to it. And then again, with time, a mathematician figured out, wait, I can define what the square root of -1 is. I'm going to call it I, and developed a number system based off of that. So if you square I, since I is the square root of -1, I squared is -1. For the complex number A plus BI, if B equals 0, that would mean it's just A plus 0I, which is A, which is just a real number. If B is not equal to 0, then you have a complex number. Sorry, just reading an email about what's going on with the attendance. So my plan is what I'm going to have to do. The number A plus BI, if A is equal to 0, is purely imaginary. The set of complex numbers consists in the set of real numbers and the set of imaginary numbers. Yeah, this is just very technical mathematical terms here. Two complex numbers, A plus BI and C plus DI can be written in standard form. Are equal if A is equal to C and D is equal to B. So basically, hey, if I have 2 plus 3i and this says 2 plus 3i, they're the same number. Make sense? So again, this is all much more technical parts of the vocab. Let's get into the work we're going to do with these. To add imaginary numbers, you're going to add the real parts and you're going to add the imaginary parts together. Same with subtracting. The additive identity inside the complex number system. So the additive identity is, hey, 1 and -1, that's an additive identity. 1 plus -1, 0. So it's saying, hey, if you just change the sign to everything negative here, you have your additive identity. Basically, they'll cancel out. Let's look at this in action. Think of this just like combining like terms. I kind of looks like a variable. Technically, it is a number that is equal to the square root of -1. But if you think about it like an x and go, oh, I'm going to combine like terms here, you'll do everything correct. Nothing will go wrong thinking of I as a variable right now and treating it as such. So that's what I'm going to do. I'm going to start here. Let's distribute this negative sign. So that gives me 5 minus 6i minus 3 plus 2i plus 4i. Let me recalibrate my board. It is running a little bit off. So now what we're going to do, hey, I have real parts. I'm just going to add those together. Then I have imaginary parts. Those are the parts with the I. I'm going to then add those together. So those can combine. 5 minus 3 gives me 2. And then my i's combine. -6 plus 2 plus 4. Oh, wait, they all cancel out, giving me 0i. So actually in the end, this is just equal to 2 because all my i's cancel out. Make sense? Like I said, this is just like combining like terms. You think of I as a variable, it's not going to get too crazy on you. There are just some important things you do have to remember about it, and we'll get into those details with multiplication and division. Because anytime you have an I squared, that's actually going to be -1. So you're going to have to replace anytime you see I squared with -1. So to multiply to imaginary numbers, we're going to use FOIL. When we get an I squared, we will plug in -1 for it. That's a big important fact with multiplying. You guys know how to FOIL. You saw it from at least integrated math 1, hopefully integrated math 1, but you at least saw it in integrated math 2 and integrated math 3, how to FOIL, how to multiply something like this out. So that shouldn't be unfamiliar. We just have to remember this fact here. I squared will become a -1. Okay. So in case you're forgetting FOIL, I'm going to do it the longer way where I actually write out the word FOIL. If you're going Isakov, I've done this, I get this. I don't need to write FIOL to know how to FOIL this out, how to multiply this out. That's fine. If you can do it with just like drawing your arrows or just distributing, that's fine. I'm doing this in case somebody's forgetting a little bit, okay? So 5 times 3, 15. 5 times -2i, -10i. My inners, 6i times 3 will be -18i. And finally, my last, -6 times -12i will be a +12i squared. So here with this, these are like terms. We can combine those. And this actually becomes 12 times -1, meaning this is actually -12 back here. So I could have like 15 minus 28i minus 12. I go, oh, wait. Here, these are like terms as well, right? 15 minus 12 is actually just 3 minus 28i. Okay, I'll redo it without using the FOIL part, okay? We'll get the same answer. So like if I'm just multiplying them out, so if somebody said, let's complicate it with the FOIL, I'm going to leave the FOIL up there for just a brief moment in case anybody was copying that down. I'm going to redo it without writing out the FOIL part if that made it look complicated. Okay. So without the FOIL part, again, I'm just multiplying in that same order. So 5 times 3, that was 15. 5 times -2 was -10i. This will be a -18i for my inner. And then my last, -6 times -2i, for both of them will be a positive 12i. Well, again, I notice, oh, not 12i squared. Since that's a 12i squared, this will actually become -12. Because the I squared, this is really 12 times -1. So I said, oh, that's actually -12. That's the big thing to watch out for here. Combine these, combine these. 5 minus 12 is 3. -10 minus 18, -28i. A little less complicated that way. Again, I showed that structure of FOIL in case some of you still needed it. But if skipping that FOIL structure going straight to here makes more sense to you because you practiced it enough, go right ahead. Be my guest with that. That's absolutely fine. But that is multiplying. Okay, let's take a look at the last idea with the complex conjugate. So, the product of complex conjugates is a real number. So when we multiply by a complex conjugate, it should become a real number. The imaginary part should drop out. That's the point of our complex conjugate. So to find the quotient of a complex number, a plus bi and c plus di, where c and d are not both 0, multiply the top and bottom by c minus di. So actually, let's see, time-wise. Yeah, actually, time-wise, I'm going to quickly show you, go a little deeper into this than I initially planned, and show you how that works from this standpoint here. This is from simply the theoretical standpoint. We're actually going to see it in motion without all these variables in it. What I need to do is multiply by c minus di and c minus di. What's going to happen is we will get things to cancel. Yeah, I can very quickly do this. I'm doing this super fast. This is going to be a times c minus, or no, sorry, plus No, I was right. Minus, sorry. Minus A times DI. Then that's going to be plus BC times I minus B times D I squared all over C squared minus C times DI plus C times DI minus D squared and I squared. Those conveniently cancel out here. If this is confusing you, please don't stress it. This is simply showing how the imaginary part disappears from more of just any old form. We're going to see it with numbers in a minute. So if it's confusing you without numbers, please just go, okay, this is a little confusing with just variables. I'll deal with it with just numbers. So this ends up being AC. Now this part becomes a positive B times B minus AD times I plus BC times I all over. Now this I squared becomes -1, making that a plus C squared plus D squared. And you notice that my I leaves the denominator. There's no more I left here, just only in the numerator. Again, if that looks a little confusing, please don't stress what I did here. We're going to see it with real numbers, and it's going to make more sense with real numbers in one moment. So let's actually do it with the real numbers now. So this is 1 plus I over 2 minus I. Okay, first thing I need is my complex conjugate. This has a minus, so I change it to a plus. To plus I. 2 plus I is going to get us basically that difference of squares happening, so our i's will cancel out on the bottom. Whenever I multiply the denominator by, I also multiply the numerator by. Now it's just a matter of multiplying this all out. So again, just doing FOIL here, 1 times 2 is 2, plus 1I, plus 2I, and then I times I will be plus I squared. Now that I squared is going to become a -1 in a second. Now let's also multiply out the denominator the same way. 2 times 2 is 4. 2 times I is plus 2I. Now do the same thing with the negative I. So I'm going to be a -2I. And negative I times a positive I will be -I squared. Any questions about this so far? Okay. Now it's just a matter of cleaning this up. So I squared, this becomes a -1. Now this I squared, because it's already a minus in front, will actually become a +1, and these will cancel out. So this becomes 2 minus 1 is 1. 1 plus 2 is 3I. 4 plus 1 is 5. And notice there's no longer an I in the denominator. So one thing we do not like in math is to have square roots or imaginary numbers inside denominators. So that's why we rationalize this. So So through rationalizing with the complex conjugate, we get rid of the I in the denominator. If we were to go on the complex plane and see these, we'd see they are the same points. So, last thing here, we're using the quadratic formula. If you get something like the square root of -7 inside of it, there are no real numbers at work. But we can factor out an I, or the square root of -1, and make it a complex number. So if A is a positive number here, so basically what we're saying, square root of -7 is I root 7. Square root of -A is equal to I times the square root of A. So if you ever have a negative trapped underneath your square root, you can literally remove the negative sign by putting an I in front of it. That if it was a number like square root of -16, that'd be I root 16. Oh, wait, the square root of 16 is just 4. So we could call that 4I. And that's it. What we have for homework is just a series of questions. We're doing 22 through 28 even, 32 through 36 even, and 52 through 56 even. If I recall correctly, this should be adding and subtracting. This group should be our multiplying, and this group should be our complex conjugates group. If I recall correctly, and I looked on Wednesday, so it's been a little bit since I looked, but it should just be practice with those ideas. So I'm going to stop recording. Stop recording.